So for the penultimate talk for the conference, we've got David Stephen from Quantinuum joining us. So yeah, thank you. Take it away.
Yeah, thank you. Thanks everyone for being here. And it's really nice to be at this great conference. And thanks especially to Marcus Frems for making me not have to talk in the morning. I was very happy he graciously swapped with me. So yeah, I just started Quantinuum in October, but this is old work. So this is the only instance of Quantinuum teal you'll see on my slides. So I will not be using the official slide style. But I am happy to talk about what we're doing there at any point if anyone's interested. So I'm sorry for the kind of stupid title, but I'm going to talk about a scheme of quantum computation that we ended up coming up with in this paper, which had a very strange set of elementary gates. And we had to figure out how to use them. And we learned some interesting things along the way, which we followed up in this paper. And so the kind of gate sets I'm going to talk about are like this. And this is actually, I just love this picture. I try to show it whenever I can because it's like a representation of our quantum computing scheme, and it looks like a computer chip. You know, it's really cool. I would invite you to think of a universal gate set. Maybe you think of something like Hadamard's, T's, C naughts, or if you're more towards the physics, some sort of actual interaction generated gates. Or maybe Hadamard, Toffoli, and so on. Obviously, there's many universal gate sets, but I think almost all of them people would think about or write down have the same property. They have this kind of local translationally variant structure, and what I mean by that is you have these kind of small local gates. So like when I say C naught, I mean I can apply C naught to any pair of my qubits, so I can kind of translate it all around. And the universality kind of like almost follows from the fact that just on small systems it's universal, and then you're just like tiling this thing over and over again. So like understanding universality on growing size systems is very easy. So like most gate sets will be defined in this way. In fact, I think VQP is basically defined by having this kind of local translation invariant structure, the complexity class. But what I want to ask today is what about gate sets that don't look like this, that don't have this kind of local translation invariant structure? And it doesn't have to be translation invariant, but yeah. Where do they come up? What do they look like? And how can we use them? So just to give maybe a couple examples I could think of where I've seen this, you may have some physical architecture constraints. So there was a paper by Rossendorf in 2005 where he showed even if you have only these kinds of gates where kind of you apply like basically a CZ or like a ZZ type interaction to all of your qubits at once on a 1D chain. So you cannot selectively address them, but it's just all of them or none of them. And you apply the same Pauli rotation to all your qubits on the chain at once. So this is like totally, okay, this is translation invariant, but not in the way I meant before. This turns out to be a universal gate set. So it's quite surprising, I think. But you can show, for instance, that you can efficiently implement, Hadamard, T, and C naught, that gate set, and therefore this is also universal. I'll try to argue that that's kind of not the smartest way to use these exotic gate sets is not to just reduce them to the boring ones. But yeah, so one example you might not have this nice structure is if you have some physical architecture constraints. And sorry, the constraint here is that you can only say send a laser beam through all your atoms at once or something. So like you have to address them all at the same time. But you might also have constraints looking at QEC codes. So of course, if you have a bunch of surface codes or something with one qubit in each of them, you will have this kind of one transversal gate on each one, and you'll have a transversal CZ between all of them or something. So you'll kind of recover this structure I talked about. But when you consider high rate codes, it turns out that the easy gates you can do, like the transversal gates, don't always have this nice structure. So this is just one equation I copied from this paper. I think it's a transversal gate of some bicycle LDPC code. And it's just like some weird product of CZs, and this is kind of all you can do. I mean, I'm sure there's others, but this is an example of one thing that, you can do this whole product of CZs, but you can't just do that one, so you don't have this, you can't break your gate set into these pieces. And kind of more generally, where do you get these non-local gates? There we go. So I stole this picture from Daniel's paper. If you just take any, say, a Clifford plus T circuit, so I have these T gates here, which are these yellow Zs, and a bunch of Clifford gates, which are these orange ones, you can imagine commuting all the Clifford gates to the end and pulling them through. And when you do that, it turns these T gates, which can be thought of as rotations about the Pauli Z axis by pi over 8, it turns them into other rotations. So this one, I think, becomes this guy. So it becomes a big kind of e to the I, z, 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 y pi over 8 rotation, and so on. And once you've put your circuit in this form, it'd be great if you could just do this gate as an elementary gate. Then you wouldn't have to build it up out of all these small Cliffords. But also you can think, okay, are there more efficient ways to generate these long polystring rotations if you don't have these kind of local Cliffords in this way? But the main example I want to talk about is somewhat different, and it comes from MBQC. So I'm not going to explain how MBQC works, because I think many people will already know, and it's not really the point of my talk, but I will explain what it does. And so what you do is you start with, traditionally you start with something that's called a 2D cluster state, some entangled state on a square grid of qubits. And once you have this state, then you measure it. And depending on how you choose your measurement bases and which order you measure things in, it turns out by measuring the state, you can simulate universal quantum computation efficiently. And so here I've shown an example of like a measurement pattern. So like this is the key for these measurement axes. I can do a z measurement, x or y, or somewhere in between x and y, so in the xy plane. And if you were to measure the state like this, what the z measurements do is they effectively carve out individual wires. So you can kind of see, okay, there's 3 horizontal things going along here. And this is going to be the 3 kind of qubit lines in my circuit I'm going to simulate. And when these lines connect vertically, that's an entangling gate, and so on. So you can kind of maybe imagine how you can carve a circuit into this cluster state. So yeah, MBQC, I think it goes without saying that it was a huge new paradigm for quantum computation and for fault tolerance and many other great things it gave us. But it turns out this isn't the only way to use a 2D cluster state to do universal quantum computation. You can throw out the z measurements, for example. So this was shown in this paper, that this is still universal. So now I only have xy plane measurements in my cluster state, so I can't do this trick of carving out wires. And so I should say this trick of carving out wires effectively lets us recover this kind of local translationally invariant CZ gate set. But over here I can't do that anymore, so I don't have that. So instead, what my circuits that I implement by measuring a cluster state in this way, what they look like is I have kind of at every time step I applied this big Clifford unitary, which is CZs between neighboring qubits and then a Hadamard, and that just always happens no matter what I do. And so all I can do is by changing my measurement bases, I can insert these z rotations parameterized by some angle theta. And so again, this doesn't really, it may be surprising that this is universal, but it is universal in the sense that by choosing these angles theta appropriately, you can create any unitary on these qubits. And so not only is this kind of fundamentally interesting that you don't need these, but it was very helpful. For example, there's a scheme of quantum computation called blind quantum computation where you want to kind of hide your circuit, especially if you want to, say, send a circuit to like a quantum server and you don't want them to know what you're doing. There are ways to do that using measurement-based quantum computation, but it doesn't work if you need these z measurements, because kind of as soon as you see where the z measurements are, you can kind of see what circuit they're trying to carve out. But when you don't have those, you can kind of hide what you're doing. And also for us, it was very important. We had several papers on this idea of kind of computational phases of matter, where kind of whole physical phases of matter, their ground states were all useful for MBQC, and this result was essential for us to be able to do this. But I want to talk about is an even more restricted setting, where the measurements I'm allowed to do on all of the rows except the first one, I measure in Y, and I have no choice. I just measure in Y. And so my only options are choosing the measurement in the XY plane on the top row. So this is a very restricted setting of measurements I'm allowing myself to do. And we study it in this paper. And this turns out to simulate similar circuits to over here, as you can imagine, where now again, at every time step, I have this big Clifford unitary. Now there's also a phase gate, square root of Z, that's appearing at every time step because I measured in Y, not X. And the same thing, I can inject these kind of z rotations using my measurements, but they can only appear on the first qubit ever. So those are the kinds of circuits I simulate. And what we show in this paper is that this is universal, and I'm going to show you how that is true shortly. And I'll say just in a second, yeah, like this, again, every time you find a new way of doing measurements on a cluster state that's universal, you can kind of unlock some new applications. So as I'll briefly mention, this allows you to do MBQC in 1D. In a very natural way, and I'm going to try to argue in some way that this is actually a more efficient way of using your thetas or your T gates, kind of. Yeah, okay, so why did we consider this constraint in the first place? So imagine we have this scheme that I told you where you have a 2D cluster state and you measure all the qubits except the top row in Y, and then you have some freedom of how you measure the top row. If we do that, we can actually just measure all the qubits in the Y basis at the start because those measurements are not adaptive, so we can just measure them out, and what we're left with is some state of this top row of qubits, so kind of a state of a 1D line of qubits. And if my claim that this MBQC scheme is universal is correct, that means that this 1D state of qubits is a universal resource for measurement-based quantum computation. And it turns out that this 1D state, there's a different way of preparing it. Rather than starting with a 2D cluster state and measuring out a bunch of qubits, you can prepare it strictly in a 1D architecture where you just start with a product state, evolve it by this linear depth circuit, which is linear in like the Y extent of your cluster state, and then you get out some state at the end of the circuit, and so these two states are the same state. And so what we tried to say was that this is a very natural circuit that you can do in a one-dimensional architecture, which gives you a universal resource for measurement-based quantum computation, which is something people might have said, with certain assumptions, is not possible. And here the fact that we have this linear depth circuit where here the depth of our circuit is going to affect how many logical qubits we can compute on, that was very important. And that's kind of how we got around these hand-wavy arguments why it shouldn't be possible. Okay, but that's the last I'm going to talk about that application. Oh, that was weird. What the heck? That's the morph transition. It's powerful. So as I said, this is the kind of circuit I want to study for most of the rest of the talk. And so we have two operations. We have this big Clifford unitary that I've drawn this box around. And then we have Z rotations of the first qubit. So those are the only operations I can do. And notice immediately that this gate set does not have this, I realize the wording is confusing, but doesn't have this translation invariant structure in the sense that every time we add more qubits, the gates we can do look much different because this box kind of is growing. Like we don't just have, there's not just like one CZ that we can always do here no matter how big our system is. So like if we want to prove this is universal, we basically have to reprove it from scratch for every system size. It's not obvious if you prove it for this that it is also universal for another system size, and it turns out that it's not universal for all system sizes. And the main theorem we proved in that first paper is that circuits of this form are indeed universal for computation. Now there's this little caveat, which is actually not universal on all of the qubits, but approximately 3/4 of them. That's a technical detail, and I won't mention it again. But this 3/4 is kind of hanging out in some of my slides, but I'm just not talking about it. And moreover, if you really wanted to reduce this to the kind of circuit model with these small gates, you can do that with polynomial overhead. But again, I want to argue that you shouldn't do that if you want to make best use of this scheme. And I just want to briefly mention, I think this is a pretty cool result that this is universal in the first place. For one reason, it kind of, if you think in a fault-tolerant context, it really matches this proposed structure of having a bunch of 2D color codes with a 3D color code on top. Because everything is Clifford, and so these you can all do very easily in your color codes, and all the non-Clifford stuff very naturally only happens on one qubit anyways. So what people would have done in the past in this structure, I think, is every time you want to do a T-gate on some qubit, you have to swap it up to the top, do a T-gate and swap it back. But here, I would argue that this is a much more efficient way of doing this. Yes?
Pick the qubit for which is not universal. Do you have a choice? You say
Oh, no.
the qubit.
I see. No, it's basically the reason this 3/4 comes is in the scheme, you kind of freeze every 4th qubit to be in a fixed state throughout the whole computation. So no, you don't have a choice. Yeah. Another question?
It was related.
Okay.
Yeah. So how do we think about another key consumption load is what you mean by it's only universal?
Yeah, sorry. I'm saying if we start with this qubit, say in the plus state, so every 4th qubit in our scheme, the way the computation will go is we'll choose our measurement angles, or we'll choose we'll insert these thetas in such a way that this state always stays in the plus state, so it's never touched. But if that is true, then I can induce any unitary in SU 2 to the KE on the rest of the qubits. So I can do any operation I want on 3/4 of the qubits, but a few of them are just kind of hanging around as ancillas, basically. Yeah. Yeah?
Do you think this 3/4 factor is something you cannot do better than?
Yes. In general, yes. There are some cases. So the full set of gates you can do on this whole space is a very strange function of k. This is a lower bound. Yeah, sometimes you can do it on all k, but only on a very yeah, only for some values of k, which is how many qubits I have. So.
And is the k-squared overhead coming from the fact that this has to be depth k or something? Or what do you mean by simulated with at most O k-squared?
Yeah, what I mean is basically, yeah, it's basically you get a depth overhead of k squared. Yeah. And okay, one other thing that's interesting about this is it kind of shows that you only need to be able to do one Clifford gate to be universal, and it's this Clifford gate. So like if you have some code that can do this whole thing, treat it as one big unitary transversely, and you can do magic state injection, then it's universal, kind of. Which again, like I'm not saying you can do C naughts transversely between all pairs of qubits. I'm saying like there is one unitary matrix. If you can do that one matrix transversely, then you're done. So I think that's also an interesting idea. Okay, so now I want to go through the proof briefly of how you can show that this is universal, and that's going to lead us in a totally different direction for the rest of the talk. So it's kind of, yeah, you might ask, how can this possibly be universal? Because all I can do is kind of equally address all the qubits with this thing, and you know, selectively address only the first qubit. So how can I possibly selectively address the other qubits? And so the way we do it is you can kind of get spatial control from temporal controls. And it turns out what happens is and so, okay, I shouldn't say when measured. So this language is for the measurement-based quantum computation paradigm. So depending on where I insert these angles theta, they do something different logically to my information. Because as you can see, for example, for k equals 1, my big Clifford box is just a Hadamard times a phase gate. And so the kinds of circuits I can do look like Z rotation, HS, Z rotation, HS, Z rotation, HS, and so on. And so similar to on the second slide, I can pull all these Clifford gates to the end, and HS cubed is the identity. And that conjugates these gates. And so it turns out that this sequence of gates is equivalent to doing a Z rotation, and then a Y rotation, and then an X rotation. And these are, of course, universal for one qubit. Right? And so that's what I've drawn here is, yeah, if you imagine this chain, yeah, okay, so maybe it is useful to think in this measurement-based quantum computation of like I'm measuring the different spins in the chain, but this is also just the different positions of inserting my Z rotations. This is like when you measure the first chain, you induce a Z rotation. The second spin, you induce a Y rotation. The third spin, you induce an X rotation, and so on in this repeating pattern. And yeah, and so this is universal on one qubit. When you go up to 3 qubits, for example, so now I'm drawing this plot. I have 3 rows to this plot. This is my 3 logical qubits that I'm computing on. And so this is saying that when I measure the first spin in the chain, or if I inject a Z rotation at the first time step, I induce a Z rotation of my first logical qubit. On the second spin in the chain, I get a YZ rotation on my first 2 qubits. The third one, I get a YXZ rotation, and so on. And so each row here represents 1 qubit in my system, and each column is a Pauli operator defined in that system. Okay, so this is just a bunch of Pauli operators arranged in a table. That's what these pictures are. I'm going to be showing a lot of these pictures, so if it's not clear what it means, please let me know. And so we can try to do the same game. Okay, if I take all of these different rotations and I compose them cleverly, can I induce any unitary on my 3 qubits? And in this case, it turns out the answer is yes. But you can see going from k equals 1 to k equals 3, I have a totally different gate set. It's not like for k equals 3, I have 3 copies of this and then some other stuff. When you go up to very large k, you get this cool fractal pattern emerging in these operators. And so again, here, now I have 31 qubits in this example, which is the 31 rows of this table, and each column is a Pauli operator. And so like one of my elementary gates I can do is this giant Pauli string rotation that's like X, I, Y, Z, Z, whatever. And so you can say, okay, if I can do all of these giant Pauli rotations, e to the I theta times this Pauli string, can I do any computation on my logical qubits or not? So that's the game we have to play, and you can see how it's kind of a different game for every k because the shape is not growing nicely with the system size. Yes.
I just want to make sure I actually do understand.
Yeah, thanks.
3. So the squares there are indicating the unitaries that are performed on those qubits in those time steps.
Yes.
So what is the corresponding? So this thing you're showing us in k equals 3 is the result of a particular sequence of thetas applied to the top row.
Yeah. So this is saying if I go back. So yeah, thanks for giving me the chance. So think of this picture, but just with the top three things, and think of all these thetas, and then I'm going to pull all of the Clifford gates to the end of my circuit, and that's going to transform all of these thetas, which are currently z rotations of the first qubit. It's going to okay, yeah, like this guy's going to turn into like a yz rotation. This one is going to turn into like a yxd rotation, and so on. Okay, so that's what the columns of this plot are the different rotations that I get in this gate set after I pull all the Cliffords through to the end. Okay.
So that means that in this diagram, some of those, so there's only a set of thetas, there's 3 thetas in that picture, right?
Yes.
So that means there's I get 3 continuous variables to specify the unitary.
Yeah, yeah.
So in the diagram.
In this diagram, I'm considering a deeper circuit.
Yeah, I'm considering a longer, but actually, so the point is that when you were indicating that, on k equals 3, there's certain rotations about certain axes.
Yeah.
That will be determined by the choice of theta along the top.
Exactly. And so if it's like, okay, I've compiled using this gate set and I want to, at some point in my circuit, do an X rotation of the third qubit, then you would set, all the thetas to 0 except for the one in this, in this part of the chain, and you would do a rotation there, and that would correspond to this rotation here. Yeah.
Right, but what if I move one step to the right? There are 2 different non-trivial unitaries in a column, right?
Yeah, yeah. So that means measuring the fifth spin or injecting it, does an X rotation, and the 6th one would do a Z rotation.
And okay, so the 7th one does a Z rotation and a Y rotation by the same.
A ZY rotation, not a Z and a Y, but like a multi-qubit rotation. Yeah. Yes. Thank you. Yes, thank you. My gates are the exponentials of polystrings, and the columns are the polystrings. Thank you. I appreciate thanks for asking, because I'm sure it was not clear. Yeah.
Does it also determine what you can measure out at the end? Like those are the bases you can measure?
You can measure in the Z basis always, basically. So it's
effectively measure these transformed operators if you keep measuring and doing the circuit, or just measure everything out at the end.
Are you talking about like pushing all these Cliffords to the end? That's going to be doing some weird multi-poly measurement, or
Well, your circuit, you want to measure something out.
right. So what happens in the scheme? Well, it's just a circuit. I can measure it whatever I want. I'm not sure. Or like in the MBQC formulation of it, what happens is at the end a Z measurement happens. A measurement in the Z basis of all qubits. If you're just running the circuit, you can measure whatever you want. I'm just talking about a universal circuit. Yeah.
Yeah, sorry. You mentioned that you had to ignore every 4th qubit.
Yeah.
Something like that. How does that manifest here in these diagrams that you're showing?
Well, right here I don't have 4 qubits, so I can't show you. But what's going to happen is that eventually in my proof of universality, I'm going to only choose the columns of these plots. So those are the only gates I'm going to do, such that it acts as like an X on on every 4th qubit. And so then I can effectively ignore those X's, and those qubits just stay in the plus state if they started there forever, kind of. So that constraint is going to affect which columns I'm actually allowed to use in the final scheme, but that's a very technical detail.
Is that related to the fact, I would naively think that in order to get universality, you need X, Y, Z for every logical qubit that you want, which is basically 3 to the K number of different polystrings that you need to be able to access.
Yeah.
But you said that you can do this in constant, some polynomial with K depth.
What I'm saying is that I can simulate, if I really want to, I can simulate, CZs, Hadamard's, and T's with the polynomial depth overhead. I'm not saying I can do any unitary in polynomial depth. No, because that would be obviously too powerful. Okay, so I should move on. So yes. So thanks, Stephen. Yes, my elementary gates are big exponentiated polystrings, and I need to say that the set of all these exponentiated polystrings is universal. So now this is kind of shifting now into the second paper, where we studied exactly this problem. When does a set of polyrotations, so exponentiated polystrings, generate all unitaries? And the key fact is that we can actually get more strings than just the ones we start with. So for example, and this is based off the fact that if I can do a rotation about a polystring Q and P, then by doing this sequence of rotations, I can effectively do a rotation by the commutator of P and Q. Now, of course, if P and Q commute, then this just does nothing. And so I only kind of get a new rotation if they anti-commute, right? And every polystring either commutes or anti-commutes. So for example, just on one qubit, if I can just do X rotations and Z rotations, by doing this sequence, I can do a Y rotation. And that recovers the fact that we know that for one qubit, even if you can only natively do X and Z rotations, it's still universal, because you can effectively build Y rotations through commutators of these gates. But like I said, if they commute, then you can't get this. So if I can do an X rotation and a Z rotation, I can't get a Y rotation from these because they commute. So only when they anti-commute can I build new rotations up. And so I'm going to say that a set of poly rotations, so a set of polystrings, is universal if you can generate all possible polys using commutators and maybe commutators of those commutators and so on. Because that means if I can generate all polys using commutators, that means I've generated all of SU 2 to the K. And so one example of a set that does this is what I would call how you'd understand the standard gate set in this language is the poly rotations I can do are about the x-axis for every qubit, the z-axis for every qubit, and then like neighboring ZZ. So these are like your single qubit gates. These are like your CZ gates, or like a continuous version thereof. And so you can see how from these things I can build other polystrings. So by taking this commutator, the commutator of Z1, Z2 with X2, I can get a ZY rotation. And I can take that ZY rotation and do another commutator with Z2, Z3, and I can get a ZXZ rotation, and so on. And you can see how I can kind of build up every polystring in this way with this gate set. And so the question is, given some set of polystrings, can I build every polystring by taking the sequence of commutators? Okay, so that's the problem I'm going to be thinking about for the rest of the talk. So then we say, okay, the way we answer this for our gate set is by taking commutators of the columns of this plot, can I generate all polys? A simple question. Yes.
Sorry, so this is sufficient, but is it necessary?
Well, this is necessary if you want your rotations to exactly generate all of SU 2 to the n. It may not be necessary if you just want to steer some initial state to some final state, kind of. So it depends how strongly you want to do your computation. It is necessary if you want to fill the whole unitary group. Yeah. And another thing is, even if we prove it's universal, and so let's say this is universal, which it is, and say it's okay, I want to do a Z rotation about my second qubit. So that's none of the columns of this plot. So I'm going to have to compose these elementary gates to get that. And it's not obvious how to find that, the way to compose these things, as I will talk about later. And so there's kind of a compilation problem that shows up. And also you can ask, okay, how long do these sequences need to be? Because if I need to take some giant sequence of a bunch of commutators to get anything, that will give me a very bad overhead to my scheme. And so that's where these poly overheads are coming from. So this is kind of a generic way of doing this and saying, okay, given some poly strings, what's the full set of poly strings I can generate by taking commutators? And you just do it in a brute force tree fashion. So I start with some poly string. I consider all of its commutators. Some of them will be 0, but some of them will be non-zero, and that will give me a new polystring. And then I consider all the commutators of those commutators, and again, some of them will be 0, some of them will be non-zero, and also I might find repeats, and so I might find a poly that already appeared elsewhere earlier in this process, and so then I won't put it there. And so I continue in this way, and at some layer, I'm not going to find any new polys. And that's how you know you're done. You've filled up the entire algebra, and then you can look, okay, does this tree have all polys or not? If it does, it's universal. If it doesn't, it's not universal. And so doing this procedure, it determines the algebra, which is to say it tells you if it's universal. And also, every poly is going to appear in this tree, and every location in the tree specifies a sequence of commutators. And so it's going to tell me if I want Z2, how do I build it? Well, I follow the tree up. And also every poly is going to appear as early as possible. And so it actually gives you an optimal sequence of doing that. So that's great. But the problem is that it's exponentially costly to build this tree. There's 4 to the n poly operators. So I don't want to have to build this tree every time I want to compile my gates. And so the question is there a way of telling it's universal without building this tree? Is there a way of finding efficient sequences without building this tree? Another question I'll address is then, what is the minimal size of a set of polys that will generate all polys by taking commutators? And how quickly are polys generated, which is how deep does this tree have to go? Meaning, how long of sequences do I need to take until I've generated all polys, assuming it's universal? And how does that depend on my initial set? So these are the questions we addressed in this follow-up paper. Okay, so now let's go back briefly to my gates that I was talking about. So here is the picture of my polystrings that I'm dealing with for 3 qubits, for 7 qubits, for 31 qubits, just a few examples. So using just brute force, just plugging it in Mathematica, you can prove that for k equals 3, the set of polystrings does indeed generate all polystrings by taking commutators. And it's a very small problem. You can do it very easily. So I'm not going to give the whole proof, but I'm just going to sketch. Then you're going to see there's kind of some like, due to the fractal nature of this, there's kind of some like repeating structures that appear. So like this box, which is kind of like little segments of polystrings, is kind of repeating at all scales, kind of. But that doesn't immediately mean you're universal, because like these polystrings, yeah, they have this nice little box, but they also have all those crap up here that might screw up the first qubit, kind of. So it's really, this is suggestive, but it's not at all a proof. But if you stare at these fractals until you go insane, you will eventually realize all the pieces that need to be put together. And but the general sense, which we generalize to a larger class of sets of polys, is you can kind of have a case where you have like universality on like the first few qubits, which is easy to prove. And then you kind of use that to like everyone says I use the word bootstrap wrong, but you use that to induce the universality of the rest of the qubits. So I'm being vague, but it is a technical condition that makes this work. But I will say, by kind of using these repeating structures, we can indeed prove that this set of polys for all k, by taking commutators, you can generate all polystrings which have identity or x on every 4th qubit. That's where that 3/4 comes from. So like almost all polystrings. Yeah, and one sec, Dom. And furthermore, our proof is constructive. So the way we show it is actually we defined an algorithm that will take any polystring and find you a sequence to realize that polystring. And we prove for a certain set of polys satisfying some condition, which these always satisfy, this algorithm always works. So it'll always find you a sequence that gets you to any poly. And so this algorithm has like computational complexity order k squared, so it's polynomially easy to do it. It's not exponentially hard like building the whole tree. And the length we prove is at most linear in the number of qubits. Okay, so like we don't have big long sequences of commutators. They're only at least length k, well, or 4k or something. And this is the kind of the optimal scaling that you can hope for. Yeah, Dom.
Well, I was just going to ask, so in these like gaps where you don't have boxes,
Yeah.
is the idea that they always get hit by x's by the following, like squares that are further down? So
Yes, exactly. So like every column that has a red box in it, those are actually the only columns I use, and you'll notice that they always act as x on every 4th qubit, kind of, which is again something that you can prove with this fractal structure. Okay, so this is all I'm going to show of the proof of universality for this case, but I did say there is kind of an algorithm that we constructed which is very generic. Well, not very generic, but it works more generically than just on this set, which finds the sequence of commutators, and that's our proof. And I'm going to show you an example of this algorithm and why there's some subtlety to it. So it's not such an easy problem to find the sequence of commutators. So yeah, the goal is, given some set of polys, here's my generating set. I just picked a random set. This isn't universal, I think, but it doesn't matter for this demonstration. Given a target poly that's like in the algebra generated by these, find the sequence of commutators of the generators that gets you there. So that's what the algorithm does. And so let's say, so there's 3 steps. The first thing you do is you take your target poly and you decompose it as a product of elements of your generating set. So assuming you can do that, that's very easy. That's just a linear algebra problem. It's just solving a matrix. It's very easy to see that IYX is this product of these 3 polys from this set. And so now, like, these are the polys I need to kind of stick together by taking commutators to get to where I want to be. But I can't just multiply things. I have to take commutators, which is kind of a commutator multiplies if they anticommute, but it does nothing if they commute. So it's kind of a restricted form of multiplication. And so you see that actually these 2 guys commute, and so I can't take their commutator. Or like that won't help the sequence. But these, what's the order I did it? These 2 anti-commute. Yii anti-commutes with ZIZ, so I can take that commutator. And then the product of these guys anti-commutes with XYY, and so I can take this. Okay, so in this instance, all I had to do was decompose my poly as a product of these, and then just find some order of taking the commutators to kind of stick all these polys together. if this was all you ever had to do, the problem wouldn't be that hard. But you can prove that you have to do something more sometimes, which is, let's take now ZZI as my target. And so again, you can see it's the product of these 3 polys, but you can see all these polys pairwise commute. And so there's no commutators I can take. So it's like, well, how am I going to stick these together? Because all my commutators will be 0. So what you have to do is introduce what I call like a helper poly, which facilitates the anti-commutation. So first you take the commutator of YII with ZIZ, and then you can see that all of these commutators are non-zero. And then at the end, I kind of get rid of YII. I take that commutator again, such that my final poly is just a product, of all of these things, and so I get what I want. So it's kind of the reason this algorithm is complicated is because, yeah, you sometimes need to travel down a path, a side road for a while, inserting some polys that you don't want until you kind of get to where you want to be. But yeah, we prove for a certain class of gates that you can always find this, and so it always works. And so you can always find a sequence to generate any poly for the certain class of universal sets. And this is the algorithm, we can't prove that it always works, but even for sets with other structures, it seems to work pretty well. We found a greedy way of trying to find these helpers that seems to work heuristically. Okay. So yeah, that's kind of how we prove that these sets are universal without having to construct this whole tree every time. Is we can observe it has a structure that will allow this algorithm to operate, and therefore it will be universal. Okay, so the next question I said I wanted to address is, what is the minimal number of polys that generates all polys using commutators? So on 1 qubit, it's 2. If you have X and Z, then you can get Y, and that's all of them. On 2 qubits, it's, well, I guess it's 5, because that's what I proved. So one observation is our set has size 2k plus 1, and I'll point out, there's more than 2k plus 1 columns, but I actually don't use all of the columns in the proof. I don't use all the columns to induce universality. I only need a subset of them, namely 2k plus 1 of them for all k. So we know that 2k plus 1 is sufficient to generate all polys using commutators because of our example. And clearly we need at least 2k, because like I said, these commutators that you're taking is kind of just like a weaker form of multiplication. And there's no way, if you have less than 2k polys, you can't form a basis of like poly strings basically. And so there's no way you'll ever be able to generate even all poly strings with products, let alone with commutators kind of. So you won't even have a basis if you don't have 2k. So we need at least 2k. So you just have to prove that if you have a set of 2k poly strings, it will not generate all poly strings on your k qubits, and we prove that. And we have this example of size 2k plus 1, therefore 2k plus 1 is the optimal size. As far as we know, this is kind of a new result. It seems like a very easy question to ask, but and so we give some examples of some other minimal sets. So sets of size 2k plus 1 that generate all polys for all system sizes. So this one, for example, it has again this little kind of universal set on 2 qubits, and then the rest of the poly strings are like these big Jordan-Wigner-like strings on the rest of your qubits. And we also give an example only with 1 and 2 body polys, which is interesting that you can find a minimal set even with this restriction. Another thing I want to mention is that while we're able to prove that this set is universal, meaning you generate all polys, actually in this case, the length of the sequences actually grow quadratically with number of qubits. So I said before how for this one it grows linearly. So yeah, that's just a special property of this set. In general, it can grow quadratically, which is probably the worst case scenario, but I'm not sure about that actually. Okay, so the last question I want to address is, do all universal sets of polys generate polys equally quickly? So I'm saying, assuming you can take commutators of your polys to get everyone, are all universal sets created equally? Meaning, does this tree, how does the depth of this tree I need to make vary with the set I started with? Because if we can find one that generates polys more quickly, that's going to be like a more efficient gate set, right? And so here's an example. What I'm showing here is, once you've considered commutators of some certain length, how much of the poly group have you filled? And the 2 curves are for the standard gate set that I showed, which is like X, Z, and ZZ. Those are the polys I'm considering. And then for our weird fractal gate set. And so you can see that the the maximum length of a sequence that you need for our gate set is 2 times shorter than for the standard gate set, and the average length is 3 times shorter. And so in general, you know, assuming these things were on equal footing and you had these elementary gates generated by polystrings, ours is a better universal set because it fills the space of all unitaries more quickly. And actually, it's not a fair comparison because the number of generators is not the same for these twos. The standard gate set has 3K generators. We have the minimal 2K plus 1, but we're still faster. So even though it has a head start, this gate set is still faster. So how do we understand, given some universal gate set, how quickly it's going to generate all polys? And how can we maybe optimize this property? And so you can give a quick combinatoric argument for this. And what I want to show is that the efficiency of generation is linked to kind of how many of your generators anti-commute with each other. So I have some initial set of polys. It's saying, and I want to suppose that each generator anti-commutes with a constant fraction f of the others. You know, this won't always be true. It sometimes might be kind of less uniform, but that's what I want to assume for this argument. Then I want to kind of come up with a guess of how quickly this set is going to generate all polys as a function of this fraction f. So obviously, if all the generators commute, then you try to build this tree, then you fail, or then you stop already at the second step because you cannot ever get any new commutators, and so you're done. And so if f equals 0, you're not universal, for sure, unless your initial set was exponentially large. And if f equals 1, then it's like, okay, well then I want things to anti-commute so I can get as many polys as possible. Because then, you know, at the second layer of this tree, all of these commutators are non-zero. Yeah, like, you know, I've gotten so many new polys. But then at the third layer, I'm taking a commutator of like a product of two things, but because everything pairwise anti-commutes, you know, P3 is going to commute with the product of P1 and P2 because it anti-commutes with P1 and with P2. So in the case that everything anti-commutes, the process truncates at the third level. And again, we're not universal. So we can't have too little anti-commutation, and we can't have too much. You have to have it be just right. And so maybe, you know, 1/2 is the optimal, you might guess. And so to actually figure out what this optimal f is, we can just do a little combinatorics argument. And I think I don't want to go into the details, but it's basically just saying, given some product of your generators, what is the chance that another generator anti-commutes with that product? And you can say, okay, well, I have to count all the ways of this anti-commuting with an odd number of the elements of this, because that's what I need for it to anti-commute with the whole string, and that has this form. Again, as a function of f is what I care about. And so then we can guess how quickly this algebra is growing. So AR plus 1 is like how many polys I get at the rth plus 1 step of commutators. And we see that it should be proportional to the step of the previous layer times this anti-commutation fraction, because that's kind of how many of my commutators I can hope to be non-zero, right? And so then kind of inductively, you can argue that, okay, then the size of this set as a function of f should have this form. And this form is called like the Q Pochhammer symbol or something, where Q is 1 minus 2f, and it looks like this. So this is kind of how quickly do I expect my set to generate polys as a function of this anti-commutation fraction f. And so we see what we saw on the previous slide. If this is near 0, then it's very slow. If it's near 1, it's very slow. But the peak is not in half. It's around 0.7. And it's always a good day when you can go to the online encyclopedia of integer sequences, because this is just some known function, and its maximum, or the point that maximizes it, is known, and it has this decimal expansion, and this corresponds, to f approximately 0.706. And so if you have a set of polys and you want to generate all polys as quickly as possible, you want to pick that set such that every generator anti-commutes with approximately 70% of the other ones. It's a very interesting number, I think. And again, I kind of have abstracted to polystrings, but I'll come back to gate sets at the end and what this all has to do with that. So to test this prediction, what I did was I generated a bunch of random minimal universal sets of polys. So sets of polys of size 2k plus 1 that are universal on 9 qubits, just as an example number. And I also generated these sets in a biased way such that I could control this anti-commutation fraction. So I make a bunch of universal sets of polys with different amounts of anti-commutation amongst the generators. And then I look at how many polys have I generated, I think after 5 rounds of commutators. And that's going to give me like an estimate of how quickly the algebra is growing. And it's perfect. Beautiful. I couldn't believe that stupid argument worked so well. So we can see, yeah, this is a very good predictor of how quickly your algebra is growing, and indeed, the best one we found was around 0.7. Now we can also analyze the various examples I've given you on this plot. So this is the standard gate set. In the standard gate set, which is right here, every poly only anti-commutes with a constant number of the rest, right? This xi only anti-commutes with zi for the same I, and like 2 of the neighboring zz's, and so on. And so the anti-commutation fraction actually goes to 0 in the limit of large system size, and so accordingly we're down here, so very low fraction and also very slow growth. So standard gate set sucks. Turns out this MBKC gate set, the weird fractals I've been drawing, you can prove as the number of qubits goes to infinity, actually has an anti-commutation fraction of 1/2, which is not quite optimal, but it's still pretty good, and it's a lot better than the standard gate set, and more importantly, it's like a constant fraction, it's a non-zero fraction even in the limit of infinite system size. And there's 2 other examples I showed you at some point, and we can put them on this plot as well. So this one down here, again, things don't commute very much, and it's very slow. This one doesn't fit on the plot, and the reason is, I believe it's for example 1, I don't have this uniformity assumption. So kind of some of the poly strings anti-commute with a constant fraction of the others, some of them anti-commute with a constant number of the others. So I don't have this uniform fraction f, so that's why it doesn't fit this plot. But it's slow anyways, so who cares? So yeah, this argument seems to explain things very well, and remarkably, this MBKC gate set is almost optimal. So an open question that I want to pose right now is, how can we systematically construct optimal sets of polys, so sets of polys with this 0.7 anti-commutation fraction? I could generate random instances with that, but I would love to have a family of increasing system size that I can prove is universal and has this optimal fraction, because that would be in this very precise sense, that would be the best possible gate set to generate all of SU2 to the n as quickly as possible. Okay, so this is the second last slide. I want to say, what does all this have to do with something you actually care about? And let me remind you, because at the start, I'm talking about sequences of commutators of polys, but what my original problem was, I want to take products of poly rotation gates to go from one poly to another, to generate some poly rotation. And the way you do this, every commutator corresponds to conjugating some poly by a Clifford operator, because a pi/4 rotation by a poly string is a Clifford operator. And so these commutator sequences that I've been working so hard to build, they translate to sequences of Clifford operations that will say grow, a Z string into any poly string you want. And so everything I've said about doing this as good as possible translates to, I want to find this tells you how to pick an optimal set of Clifford gates, such that you can kind of grow poly strings as efficiently as possible with the fewest number of gates. So here, for example, if you wanted to grow the Z string to a ZZZZ rotation, you would normally do it with the C0 ladder, if you had kind of the standard Clifford gate set. But what I want to argue is that if you pick your Cliffords from these weird, if you pick your Cliffords to be these weird polystring rotations, you can potentially generate these big rotations more efficiently, meaning you need fewer Clifford gates. And so for QEC codes, this kind of shows there's no reason to if you're trying to find some transversal gates, don't try to find just boring C0s. And for some high rate codes, like I tried to argue, you can't always get that anyways. We should be more clever about how we're picking our Clifford gates, because in that way we can optimize this, and we can optimize it in 2 ways. We need fewer kinds of transversal Cliffords in total, because I proved this fact of the minimal size of the set of poly strings that generates all poly strings. That corresponds to a minimal size of Clifford operations that generates all Cliffords, assuming your Cliffords are just poly rotations, which is a subset. So this minimizes the number of transversal Cliffords your code needs to be able to support, and also it minimizes the number of Cliffords you need to apply in a given circuit because of this high efficiency of these certain generating sets. So this kind of calls for maybe some co-design of finding good universal gate sets and designing codes which can support them, and going beyond just the boring standard gate set. Okay, so that's it. I just want to summarize what I've talked about. I described a sufficient condition for a set of polystrings to generate all polystrings. I didn't really describe it to you, but it's in the paper. I gave an efficient compilation algorithm for how to use these polyrotations. So it's saying, okay, given that it's universal, how do I actually use it? I gave an efficient algorithm that does this. I showed that the minimal size of a universal set of polys is 2n plus 1 or 2k plus 1. I've been using k. And I showed how you can actually find certain efficient universal sets of polys, which translates to sets of Cliffords, which generate all operations more efficiently than others. And remarkably, this weird fractal stuff that I stared at for 3 weeks is universal, efficiently compilable, has minimal size, and it's almost maximally efficient. So it's crazy that we found this example that works so well, and it turns out to like almost maximize all these interesting things we found with these weird fractals. So yeah, that's all. Thank you.
So in these like sets, when they have too many commutations, they don't grow as fast on how many palettes you can access. So like the number of Cliffords you need is getting bigger.
Mm-hmm.
They're more parallelizable, right? In principle, at least. Some trade-off, like is a number of layers kind of considered?
Yeah, so I'm not thinking about depth at all in these constructions. I think it also, like, if you have two big polyrotations that commute, even if they overlap, you can do them in parallel, I think, using some ancilla tricks, right? And so, yeah, okay, I see what you're saying. If things tend to anti-commute more often, it feels less parallelizable. That's probably true and worth and something you'd have to consider if you just care about minimizing number of operations or minimizing depth. So like, yeah, it depends on like your memory errors for skate errors or whatever. But yeah, I agree that you could hurt in depth when you do this. Yeah. Yeah, Timo?
Great talk. So I really like staring at matrices, and I find it very productive usually. So great choice in doing that. And have you thought about using the same approach to find like systematic approach on constructing these generators, right? You construct these generating sets randomly.
Yeah.
Have you stared at them like for 3 weeks as well?
Well, the problem is they don't look pretty, so I don't like staring at them. But yeah, I have not. So I with my colleagues are doing a follow-up where they're trying to understand what makes these 70% anti-computation things work. So I haven't done that. We do have other systematic ways of generating universal sets for all n. I showed how this thing is it generated as like all the powers of applying some Clifford operator to a given poly. That's what these plots are. You can change that Clifford operator to be a different one, and in doing that, we sometimes find other universal sets. But I haven't analyzed the anti-commutation of those yet. Yeah. Yeah, Dan.
So, yeah, thanks for that great talk. It's very interesting. The sets that you described for, or you described it sort of as a Clifford synthesis problem.
Yeah.
Where you are determining that a set of polys is good if you get sort of short sequences to perform a certain Clifford, but not a Clifford, but rather
You're right. I don't want to.
map a poly to a single poly.
Yeah.
And that sort of, when you have a short sequence for doing that, you say that is a good set.
Yeah.
Does this also translate to a good set if you're interested in just synthesizing a multiple Clifford?
Yeah, I mean, you can. Oh, sorry, I was loud. You can. I think so, because you can. Well, okay, that's a good question. Like, you can put this theta to be pi over 4, and then this whole thing will be a Clifford operator. So like this will tell you how to synthesize Cliffords, but like it seems kind of wasteful because you have like this conjugation all the time. Yeah, I don't know. I agree. It's a slightly different problem from what I said. It's not really compiling Cliffords. It's using Cliffords to steer polys to long poly strings. Yeah, I just thought about this like 2 days ago, so I'm not sure the answer to your question. I believe it should help just with the bare Clifford synthesis problem as well, but I haven't thought about it. Terry? Sorry. Oh.
Maybe start with Katie and then, yeah, go to Terry.
Yeah, thanks for the really nice talk. So would you say in the sense that you're moving the hardness of achieving universality from being able to do flexible transversal Cliffords to being able to do
Well, this one qubit, I'm imagining just doing like magic state injection to get this, to get this, to get these Z rotations. You know, like that could just be like a T gate. You know, like you could replace everything I said with T gates, and you can just use a normal, you know, solid void Kitaev kind of argument to make it still work.
It might get a bit harder the smaller the theta is though, right? To do it in a fault tolerant way.
Yeah, I agree. But again, yeah, I think that's no more a problem for what I'm proposing than in general fault tolerance schemes, I think.
Terry?
So a long time ago, there were these results on spin chains and ALT chains where if you take any, I can't remember, they're really general theorems that you take kind of any spin, one of these spin chains and do a local Hamiltonian for one qubit, one system theory, you could get universal.
You mean like you mean your gates are the exponential of the spin one chain Hamiltonian, and then some control of one of the qubits. I see. Yes.
To some extent, it looks a little bit like that because if I just turn off your clock qubit, I've got like the street.
Yeah, exactly.
Things. I'm just wondering whether there's like a optimal spin chain that you can extract of your
I see. In the sense, yeah, good question. So one thing which I think is good, but maybe, well, I think makes the question you just asked tractable. It's important that this exponentiated Hamiltonian is a Clifford operator for all of my machinery to work, which it would not be for the AKLT example, I guess. And so then none of this analysis would apply. But yes, you could try to find the optimal, you know, poly-Hamiltonian such that it's exponential generates a Clifford, whose powers will generate these good sequences. Yeah, I agree. And yeah, since you mentioned it, yeah, there are these other results. You know, I talked a lot about how this gate set was cool because you only have to control the first qubit. Like you said, there are existing results like that, but I think this is the first one where all of the non-Cliffordness is only on one qubit. These other, yeah, so it's like the scheme I showed from Rossendorf was, you know, had a similar flavor, but that needed non-Cliffordness everywhere, kind of. So this is kind of unique in that sense. It might have nice applications because of that. So yeah, I think it's a nice property. This Cliffordness is nice to have practically, and it also might make this optimization problem more tractable, I think.
Other questions? Just on that, kind of the structure there with non-Clifford gates interleaved by Cliffords.
Yeah.
Sort of reminds me of these models where people prove like unitary designs based on interleaved non-Cliffords and Cliffords.
Uh-huh.
Do you think? I mean, yeah, I don't know if that has anything to do with universality. I assume it might do, but do you think there's, you know, can you sort of construct like state designs or unitary designs maybe by this type of model?
Yeah, I think so. Like there are these schemes of showing like quantum advantage with like shallow circuits or like IQP circuits kind of things, which rely on these like similar properties to these state design techniques. And there you might say, okay, if I take a 2D cluster state and I measure it randomly in the XY basis, the circuit I implement is gonna look like it's gonna like anti-concentrate or like whatever these properties. I think they're similar to the state design properties. And people like have proposed this and actually done this as like proofs of quantum advantage and so on. This is kind of showing, for example, that you can do that even if you only measure in the XY plane on one of the rows of your cluster state, kind of. So like it's kind of you need fewer ways to poke at your state to still make a state design, kind of. Yeah, that's the most intelligent thing I could say about your question.
Yeah, Nick.
I know you did a solution to this, but do you have any reason to believe the 70% sort of rate is really like a well-defined number? Like analytic or something like that?
Well, it is analytic from, I mean, that argument I gave, and when I showed that curve, that is like in the limit of number of qubits and number of rounds going to infinity. The optimal fraction is 0.7, and that's an analytical number. So I think it is like a universal, real number that, like a fundamental number that should, yeah. Sorry, is that your question?
I guess my question is like, is there some intuition for like why it should be 0.7?
Yeah, there's some intuition. It's basically, you know how I said when everything anti-commutes, you have this feature where when you're building this tree, at the second layer of the tree, you get a ton of polys because everything anti-commutes, but then the next layer, you get very few because you're taking commutators of like products of two things. And if you kind of have a very high anti-commutation fraction, you have this like even odd effect where like, you know, the alternating layers of your tree are big and small kind of. And basically this 0.7 maximizes the benefit you get from having the even odd effect without having the lows be too low kind of. So we have some kind of understanding like that. There's a plot in the paper showing this thing. So yeah, it's kind of, well, yeah, that's my intuition.
So I think we've gone a little over time, so let's thank David one more time. Just a few minutes break while we change over.